All right. Guess we can start off things. Hello again. You might remember me. My name's Rod Burns. I work at Codeplay and brought together these talks that are happening this week. Today, we've got a talk from Michel, who's going to tell you a bit about his experiences of porting, I suppose, a few different projects from CUDA to SYCL and using the DPC++ for CUDA backend. So giving some tips on, I suppose, performance optimization, things that he's discovered, and even a few tips about using the compatibility test, compatibility tool to port the code over in the first place. So Michel, I guess I'll hand over to you. Maybe you can introduce yourself, give everyone a bit of an idea of your background and what you've been working on the last few months.
Sure. I'm a student. I live in France, and so I joined Codeplay for an internship 4 months ago. And so I worked. I spent quite some time porting various CUDA projects to SYCL. So some of them are like, so you might know, like the Cube library, which is composed of higher performance primitives. Then I also worked on porting hashing algorithms. And I also worked for the Lawrence Livermore National Laboratory on writing a SYCL backend for ZFP, which is floating point compression algorithm implementation. And so it was I think the most challenging thing I worked on, because it was written by NVIDIA engineers, and it uses almost all the latest CUDA features, which are not really available for most of them in SYCL. So yeah, I had to write a lot of things. Then I also worked with Microsoft for Microsoft Antivirus, trying to understand why the performance of the generated code is bad. So they offer an engine which optimizes kernel computation or stencils, etc. Also contributed to LLVM to fix some bugs. And then I also worked more on not personal projects, but on personal ideas. So I worked on trying to bring the cooperative groups behavior from CUDA to SYCL, because there is a lot of guarantees the language isn't providing yet. So I was just trying to figure out how we could make that work. I've also worked on a library which allows you to perform file system I/O from a GPU from CUDA. So it works. I will talk about that later. But yeah, and then also I developed some compile time optimizer to generate stencil code that has a better cache locality. So it allows to, on the OpenCL backend, when you're targeting with SYCL CPUs, you don't have any cache side effects on your computation. And finally, I also work on non-conventional things, you can say, considering remotely kernels if they are running too late, so you can have real-time guarantees that computation ends up between has some time to run. So then I also was part of the SYCL spec working group in the company at Codeplay, so just to discuss all the issues, and a lot of fixes, documentation, things which are missing in the ecosystem. So these are the results from porting the hashing library from CUDA to SYCL. And so I was very impressed, because I often read that performance was at least as good, but when I ported the library, it was already faster, way faster than the CUDA one. So I suspect it's coming from the compiler, which is way more modern on, DPC++ is the latest LLVM build, so has more optimization. And so then I worked during the few months of the internship, I often try to come back to the project to make it even faster. And so with the latest tools I will present and findings, So yeah, so the chart isn't like up to date. So the results are better in SYCL, but I haven't benchmarked everything. So yeah. So this is the file system API I was talking about. So a project I was working on. So this came from the idea that, so I discovered that NVIDIA proposes like a QFile API and NVJPEG. So the principle of the QFiles API is to allow to store memory from a GPU, like if you have some matrices inside, directly to a file system without having to go through the CPU. So you can program the file system driver into a direct memory access like engine in the GPU and store the data. But at the beginning, I kind of misunderstood the API, exactly how it worked. So I ended up implementing something else, which I think is different. So yeah, so right here, so this is an example of my work. So you are able to set up a file system object on the host, and then you launch a kernel. So here is just a single task. And from a GPU, like this works on a GPU, this compiles and it runs correctly. So you are able to have an accessor, like a SYCL accessor, and then you can just like pass a string with a name of the picture, and it will call a codec on your host or library to perform all the I/O, and the data will be fetched to the GPU. And so you can you can load images, pictures, stream, audio, whatever you want. You can also like load binary files. So here you can see like then you can, after using the accessor to load the picture, you can store some like neural network result if you're doing inference. Yeah. And this supports also like the direct storage from the GPU to the host, and you can also bypass a lot of things. So yeah, so I won't go through all the features because it is quite a big project. So it can be found on my GitHub. There is a link later. But basically, it allows you to kind of change the paradigm, the programmation paradigm, because you're not like breaking your work into pieces. The GPU goes itself fetch the work. So you don't have to launch several kernels. You have almost no latencies because there is no like anchoring latency. There is no scheduler that will wait. You won't have to wait for data to be transferred. So yeah, so like extreme uses, you can even connect your GPU to a stream, like a pipe or on Linux, and try and fetch the data like from a camera from a GPU and in real time process it and output it somewhere else. So that works. I was able to, with latest version, to get up to 60,000 input-output per second from the GPU and a bandwidth of 18 gigabits because I'm using, you can do a lot of things like to make memory access faster. So after a quick introduction on my work at Codeplay, I will present you just very summarily how to set up a DPC++ environment with oneAPI support for CUDA and QBLAS. So the instructions aren't very clear online because there is a lot of parameters that are not documented, especially for oneDNN and oneMCL. So the site will be available later with one command set of script. You run it in your home directory, whatever you want. With CUDA 10, it works out of the box, and it will produce a deploy folder with everything set up inside. Everything will be built, so it might take some hours on the laptop. Anyway, that's the thing. And so then if you support your code, so we'll talk about DPC++ later, sorry, the compatibility tool later. But right now, all you have to do is just to replace the compiler you are using, like GCC or whatever, by the new LLVM you built, so Clang++. And then you just add the flag, the target flag, so SYCL and SYCL target. It should work straight out of the box if you don't have like weird make files. Yeah. And so finally, if you need to have a preprocessed output, you need to pass the flag SYCL device only to avoid having the device compiler that is run, because if you are if you try to get a preprocessed output from the compiler, the preprocessed output will contain the integration header that requires your code to be right and syntactically correct, which is not the case if you are writing an IDE. So with JetBrains, we were able to find out the bug, and so now we have like IDE support almost anywhere with all the single things. So to port your code, Intel provides a tool which is called DPC Compatibility Tool. So yeah, once again, sorry for the links. There's a lot of them, so it will be in the slides, but you can get up. So this is a closed source tool that you can get on their website with a license, etc. So I won't be talking much about that. I don't think there is a lot to say because yeah, pretty much does like 80% of the work. Just to translate like a code, doesn't do like any optimization. So there's some caveats. The main issue is that if you have like templated, you have kernel templates that you are submitting. In SYCL, the kernel submission will probably like take at least 20 lines, 30 lines, depending on the number of memory shared memory objects you use. It will create a lot of objects. And so if you have like several such submissions, DPCT will instantiate the kernels and then generate the SYCL code. So you will have like 50, I don't know how many times the same like 30 lines of SYCL, which will be unmaintainable. So so I had that issue. So workaround is to wrap your kernel submission in another template. So you will still have a templated SYCL kernel submission. Then there are like also parsing issues that are coming because it's based on LLVM, which is not the same as MVCC, so it doesn't interpret the chevrons in the same way. And so I will go quickly through the compilation workflow, but I mean, it's way more complex, so it's explained on the website, so there is a link. But the thing to understand is that the CUDA code is not generated at when you are building your objects files. It is generated at the end. And so, but in your object files contain just like some LLVM intermediate representation. And so in order to produce it, you need the whole, to be able to see the whole translation unit. I mean, you can't have like forward definitions of functions. You need really to have the declarations so it can be compiled. Yes, it won't link. I mean, it's not supported yet on DPC++. And so the main problem with that is that you get a very, very long link time because it's where the whole code is generated. So an advice would be like if you have a large code base, is to generate your backends like CUDA backend, OpenCL backends from DPC++ in shared objects, so you won't be paying like twice or 100 times for the, I don't know how many executors, but yeah, so it can be pretty slow. Yeah, so if you want to target an NVIDIA GPU, you need a specific device selector. So with SYCL 2020, so I will present that later, there is the notion of backend that is introduced. And so now, so that isn't supported on HipSYCL yet, but on DPC++, you can just write a device selector and check whether the backend is equal to the CUDA backend, like enum. So it's pretty neat. And so the working of a device selector is pretty simple. So it's just like a functor that ranks the devices between like minus whatever and 2 plus whatever. And so if the best device is negative, it throws an exception, given which means that no device was found. And else it chooses the best positive device. And so you can also check with SYCL ls to see the devices that are recognized by your backend. So then once you've written your device selector, I would recommend to use exception handler because as your exception should be lost or found anyway at Q restriction. So yeah, so I mean, there isn't much to say about that. So we can just copy paste that in your code and it will catch the exceptions asynchronous exceptions from the SYCL backend and yeah, C++ if there are some. So then once you've got that, you have to create a queue. So just to call the queue constructor. But so this is just why we are using a try-catch block because it can fail. We are also, so I discovered that DPC++, and it is in the spec, you can create a queue and the queue can be reported as a variable, even though there was no bytecode generated for the device or anything. So a quick workaround is like the red line here, that you can submit a dummy kernel and wait and throw. And so we'll always immediately see whether the device is really working or it's just like appearing because you forget to pass a flag, something like that. So this, so yeah, so I just want to precise that all the code I'm working, showing is linked at the end of the talk. So you can just copy so include the support library in your code and you're ready to go. You don't have to copy paste that. Yeah. So SYCL 2020 brings a lot of new features that make the porting of CUDA to SYCL way easier. And so here they are. So the first one is moving away from OpenCL, which means because OpenCL doesn't really misses a lot of queries that CUDA has, and you need for a GPU like maybe like even the maximum range or range per dimension, which is not actually in SYCL. So then, like I've shown before, there is the notion of backend that is introduced. So because you can be running on yeah, not always on OpenCL, PGA or SYCL, sorry, on HIP from AMD. SYCL 2020 also brings subgroups algorithms, which map very nicely to some of the CUDA cooperating groups algorithm. So you can do a thread communication within a warp, so SYCL subgroup. You've got also like unified shared memory, which makes the code like closer to the CUDA version, but not necessarily better in terms of performance, as it was shown yesterday. You also get like atomic references, like in C++ 20, which will be better in the future because stud atomics and SYCL atomics are deprecated in SYCL. You also got a reduction interface. So I have implemented some of the cube primitives using it, and it performs as well. I mean, there is like 1% overhead because of the back of SYCL. Yeah, and then some template deduction, which helps. So CUDA has the yeah. So that was the ZFP backend of the CUDA backend was full of CUDA primitives, and so it was kind of troubling to try to find matchings between the SYCL names and the CUDA names because they are pretty different. But I think yeah, so the CUDA names were made and the SYCL names were supposed to be more expressive. So yeah, so here we got a table containing the primitives that are mapped and can be directly like rewritten in the SYCL code without any like overhead and any hassle. And so the main advantage of these primitives is like that you can have inter-thread within a warp or a SYCL subgroup communication. So it's way faster. You are not using local memory. There is no latency. Yeah, shouldn't. Then some of the CUDA primitives are missing, and it's because CUDA, I mean, is written for NVIDIA GPUs, and they're assuming that the warps are 32 bits wide. So a lot of warp mask, etc., are written using 32 bits types, which isn't showing in SYCL. So you can have like a single, so it makes no sense, but you can have also like 64, maybe more subgroups within warp items in the subgroup. So that's why the warp size dependent primitives are not available right now in SYCL. There is an extension that was, I think, was merged a few days ago in DPC++ that allows brings a group mask type, which does the bit counting for you. So should work. But then you've got like many more. You've got new warp functions in SYCL, so I guess it's fine. Yeah. So here it's just like an implementation of how you can. I had to re-implement some of these primitives that were missing in SYCL. But I mean, like, so if you want, so in CUDA you've got like the ballot primitive that allows to fetch a predicate from every thread from a warp and to make a number out of it. So it can be like rewritten in 3 lines in SYCL. So even though it's not available, it's a drop-in replacement. You just need to be sure you're running on a CUDA device. It can be wrong. You have more than 32 threads in your work item. And so then for submitting the subgroups, you just take a SYCL item or ND item and call get subgroup, and it will act like a cooperative group and select oneAPIs for the thread of the warp. Yeah. And so just I would say the main issue with SYCL right now is that this group algorithms can also be applied to groups, so which are corresponding to CUDA grids, blocks. And so then the SYCL backend, DPC++, will be using local memory, so which corresponds to CUDA shared memory, to establish inter-thread communication, which is not documented first. And you cannot query the amount of shared memory which is used, and the performance is very bad on the CUDA backend. So I would just rewrite my shared memory. It works better. I mean, you get the native performance. So yeah, the algorithm is more like optimized for GPU. And so yeah, like this is just a quick implementation of match any, but so you can see like the assembly is very close to what we would expect from a CUDA assembly. And I mean, you've got almost like less lines of PTX assembly, so it's pretty nice. You can, you have the call to the warp primitive, which is properly translated, and everything is in line. You've got like no branches, etc. Even the code would have it runs pretty well, fast. Okay, so then when you are porting your CUDA code to SYCL, another issue is ranges. So there isn't in CUDA you've got like the dimensions like dim3, x, y, z. In SYCL it is inverted because the spec decided to match to the C-style array syntax, which means that the contiguous dimension is the last. So yeah, I mean, a lot of bugs can be found there, and even performance issues, because you will have, if you want to iterate through contiguous memory, you have to iterate through the last dimension, which not really like, should be natural, but isn't on CUDA until it is in SYCL. Then also like in CUDA, you can have like a dimension which is equal to 0. You can have that in SYCL, it will fail, at least in C++. So I won't go into the detail of how to compute the sizes for your kernel, but you should keep in mind that you are targeting heterogeneous platforms. So it might not always be the same computation as you are used to be doing on SYCL. And so even like the mappings could be different. So let's say on DPC++, a work group on CPU gets mapped to a thread, while on HipSYCL, it is a single work item that gets mapped to a thread. So you have to take that into account, because even like depending on the implementation, if you really want to have the best performance, you need to take that into account, because maybe spawning like threads on the host, like OpenCL threads, it's not very cheap. So you might want to make bigger threads rather than on CUDA more. Even like the limitation of the number of items you can put in work group changes from different implementations. So you should be querying that like always. And a bug I found always I often found on the internet is people are forgetting to check the returned value from the SYCL queries. So you have max compute units and work group size. And so max work group size can return literally anything from 0 to int max. So say cmax, which is 2 to the power 64, which will often like just overflow, wrap your computation because it is unsigned and you will fail. So you should check the value return max. As an example, SYCL returns int max. So you might not be expecting that, but it is. So yeah, and then if you are supporting code from CUDA, you should try to optimize the best block size you can have, because the occupancy parameters will be different. You won't have the same occupancy. You can have like maybe less, registerization more. It really depends on how it gets optimized. So I will be talking about that later. And so on SYCL, you can also query a kernel for specific information. So yeah, so this example, so you can use that. It's pretty useful for debugging. So this queries a compiled like SAS kernel for CUDA to know the maximum work size you can submit for the kernel. Because even though you have a maximum work size for the device, the kernel has different work sizes. Let's say if the kernel uses too many threads, or it requires like too many like stack memory, stack frame, because you don't have an infinite amount in your GPU and it can explode very fast. So that's where we can drop in your code and it will work, and we will return like the biggest size guaranteed by SYCL, which is not the biggest that works. So it might give you the best performance, but that always works. And so I found I had like some weird issue that some code wasn't working in debug mode, and it was because I was using the SYCL device queries, not the kernel queries, to get the sizes. So I think, yeah, that's not very emphasized, and so I just wanted to talk about that. And so then the biggest, I think, issue you will face when moving modern NVIDIA code to SYCL is inter-workgroup synchronization and GPU synchronization, which is not available in SYCL right now. So CUDA proposes a paradigm called cooperative groups, that allows to dynamically create groups of threads, warps of blocks on grids and devices. And so the main point is to be able to do different computation on different work groups. And so even if you've ever written like some reduction code, you know that at the end you need to join all the work items before going to the next pass and reducing like in binary and thing. And so right now in SYCL, this is done just by joining the kernel and relaunching a kernel, but that can be very expensive, and we'll see later that on the DPC++, the kernel submission is very, very slow. And so the main advantage of cooperative groups is to avoid relaunching kernels. And so, yeah. So it is currently not supported in SYCL because you have no guarantees of forward progress. The language gives you no guarantees of forward progress. So the forward progress is actually like depends on the. So what I'm saying is really like specific for the GPUs, but it depends on the occupancy. So the occupancy is a ratio of let's say the amount of work items you can have at the same time running on the GPU. And so that depends on the compiled kernel, on the targeted, model of the GPU. And so SYCL has no queries to kernel to get that occupancy, even though the CUDA driver API offers them. So should be able to implement that. Another limitation in the SYCL backend is the fact that we just, I think, when anchoring the kernel, we don't have a lot of properties, so we can add a property list, but we should need a property to say that the kernel is running exclusively on the device. So right now, the CUDA driver API is able to run some kernels concurrently, but there is no like dependency, of course. You can have a kernel that is running at the same time as a memory copy, but this behavior, let's say optimization, can can change the occupancy of real occupancy of a kernel. And so you then will lose forward progress guarantees, and then you will have a deadlock and it's terrible. And yeah. So we should be able to add a kernel launch attribute, submission attribute, which maps once again to the CUDA driver API functionalities. So that would be allowed to write like device-wide memory barriers. And even though without that, I've spent like 4 months like playing with that, and I never had like a single deadlock, because I mean it was a pretty simple code, but I was able to reproduce like cooperative behavior. But once again, I don't want to recommend that, because I don't know how it will work on your driver. So yeah, I think it's something that can be addressed and can be implemented right now as maybe an extension on DPC++. I mean, I would like someone to make that. So I won't spend a lot of time on that, just the mapping of CUDA atomics to SYCL, so maybe not very well documented. So in CUDA, so in CUDA you've got 3 types of atomics. You've got system-wide atomics, groups atomics, and device atomics. And so in SYCL 2020, you are able to port them very easily. Just you need to change the memory scope. So here I've got the correspondences, and just you can drop and paste that code anywhere you want, and you can port your atomics pretty easily. And so yeah, I'm not sure how DPC deals with that, because once again, one issue is that you've got that are like spread in different namespaces depending on the implementation. Like SYCL has the right namespace, DPC++ has the wrong namespace, so you need to change the namespace depending on the implementation, which is not fun, but I don't see a point because it was, anyway. So, and I will end up the part for porting like CUDA features to SYCL on debugging. So SYCL offers, since like, I think a week, 2 weeks, support for printf functions. So you can have regular printf within a kernel. So it's nice, but it's not portable at all because it's a DPC+ extension. So SYCL offers the SYCL stream interface to, it's like a state stream, but not the same, it's a copy. And I don't really like it because it requires you to pass a SYCL stream object through your whole like code hierarchy, and if you've got like 50 like function code nested, I mean it's just a mess. You have to refactor everything just to debug. So I would recommend printf, and then you can also try maybe if you've never used SYCL. It's very nice. It works very well, and it has an openapi backend which can be parallel and debugged. With GDB, you have like to use an NVIDIA debugger or OpenCL debugger. Yeah. And so I was talking about oneAPI and OneDNN. The only caveat when you are putting some code to that is just you need to change the namespace, because QBlast doesn't implement raw major operations. It's only column major. So once again, that's not documented. The only documentation you can find is for Intel oneAPI, which is not oneAPI. There is a proprietary version. So yeah, I mean, it's you've got the namespace, the setup script, setups everything for you. Once again, there's a lot of not documented things which are which work like out of the box. And if you want to use CUDA 11, you've got a pull request in process of being merged that will add support for that. And OneDNN already supports CUDA 9, the last one. Okay, so I guess you are familiar with the GPU like memory model. So you've got like constant memory, global memory, shared memory, local, which is not defined in SYCL, but it's like more like a stack frame that can be accessed, but is private to a thread. And then registers. Yeah, and so in SYCL you have mappings to most of them, which you can access through when using buffers. So yeah, I don't really have much about that. It was well covered yesterday. So yeah, we go next. So SYCL 2020 brings unified shared memory, which is pretty nice. And but I'm not very happy with the wording of the spec and the implementations of the introspection queries. So as an example, in the ZFP backend, I had to try to infer where memory was allocated with a pointer. So I just get a pointer from somewhere because the API is written like that, and it's it maps to an C APIs. C APIs. You can get. I should use a side channel thing to pass the context, but I can't. So it's unfortunate in SYCL you don't have a default context. So if you've got a pointer, you can't like even think. You can try to construct a context and test the pointer on that context. So yeah, so that's unfortunate. But turns out the CUDA backend has only one context, or had only one context. But the other issue is that the spec is not clear on what the kernel introspection queries should be returning if you are querying a wrong context where the device wasn't allocated. Because the spec says that you can query you can pass a context and a pointer, and it returns the device from the context. But let's say you pass a host context and a pointer from GPU. Well, it will always return that it was allocated and it is a host pointer, which makes no sense. Yeah, because the implementations do not track the host allocations. But they could, because they're already known for other backends, but they don't. Yeah, so get pointer type, get pointer device work. If you have the right context, if you want to try to see whether it was allocated, probably it will return the wrong result. So they are kind of useless right now. Not very portable, let's say. So for the host, you can have a workaround using Linux kernel codes to see whether it was really allocated, like if there was a allocated, that's dirty, but that works. So fills the gap, but yeah. So something else I had to do, so can be useful, is to wrap your unified shared memory pointers in smart pointers. So like in unique pointers and shared pointer. Don't use shared pointers, so just talk about the unique pointers. But basically, like you can write a functor, which is a deleter. So maybe SYCL 2020, C++ 2020, right now you'll be able to have evaluated lambdas, so you'll be able to write that using lambdas, but right now in C++ 17 you can't. So it's just a syntax for a simple functor that will be called by the smart pointer on destruction and will free your memory. And so then you can wrap everything in it's not really nice to do that, but you can inherit from a stud object. And add more information to your memory, because right now the issue is pointers, like they don't come with size information. So you just inherit from a unique pointer. So yeah, you've got a syntax to do that. So once again, the code is available in the support library. But the point is you can add like metadata to your your USM Smart Pointers. So then you can get like a multi-pointer that gets a SYCL multi-pointer that has the right address space. So you can like even do prefetching on these pointers from a kernel. You can get SYCL spans, so which are stud span. So it's just like a pointer with a size, which allows to have more type safety. So you can have an algorithm that checks whether you are doing out-of-band accesses or yeah, a lot of very interesting things. And type safety that is brought by C++ 20 can be replicated using that API. And so then it behaves like a smart pointer. So it will free up the destruction, it has no copy constructor, etc. It works pretty well. Something else I was faced, so I know that SYCL implements support devices, I think, but at the time I did not know, so I tried to make that myself. And so I realized that the hashing library was very compute bound, more than memory bound. So, and it was like embarrassingly parallel. So the first idea I had was to, I have a few devices in my computer, and so I want to run a single computation of all of the devices because they don't need to communicate between themselves. And it turns out the SYCL spec isn't very nice if you want to do that. The main issue comes from the buffers, which are blocking, and especially if you have constant buffers for constant data or things like that. It's unclear whether they should be blocking or not, and turns out some implementation like SYCL and DPC++ have blocking destructors, while ComputCpp has a non-blocking destructor for your buffer, so which makes no sense. So then there's also the whole issue of resource management. So it's a little bit long, but at the end, what I ended up doing was creating like a handle structure that handles like the running state and acts like a state future or a SYCL event. So you can wait on that structure to be sure like all your asynchronous computations have finished across all the devices. When that handle goes out of scope, you can join the kernels, free memory, check catch exceptions, silence them because you don't want to throw any disruptions. A lot of things like that. So everything is once again available on GitHub, the whole implementation. And this is you have an example with the SYCL hashing library if you want. And so yeah, then you are just able to launch in parallel on the CPU on two CPUs. If you have, SYCL allows you to spread the workload given like NUMA nodes, so you don't have that. So it's very like nice. So yeah, a big issue I think if you are coming from CUDA to SYCL is the memory, so the local memory and constant memory, which have not behave in the same way, of course, because they're not the same hardware, but they don't have the same semantics like of accessing. And so you will end up with way different optimizations. And so I won't go like into much detail because it's already I spent too much time on that. But it turns out I'm implementing right now in an LVM some attributes you can declare a struct with, which will ensure you've got a great padding for your memory structures. So you get like, there is a benchmark to get like 3x performance improvement just by using this formula, which avoids any bound conflict. And then like, there is also an issue with constant memory. So in SYCL, so in CUDA, you can have like a global static array that contains static constant data that you use between your threads, etc. But that cannot, and so the memory will be inlined because you have a pragma unroll. And so, yeah, so you won't have like constant accesses to the uniform buffer. But in SYCL, given the fact that you need to use a constant accessor, the compiler isn't able to see through that. So you are losing inlining of constant memory. So you could be declaring a local array, but if the array is used, you have to use micros, etc. It's not fun. So okay, it's pretty late. Sorry. Sorry, probably skip some things. So yeah, so for optimization and performance tips, so a big issue I had, and there is like actually in LLVM and DPC++, is the unroller is very conservative. So I read in the doc that like turn the unroller to be like more aggressive on GPUs, but it's very like it almost like unrolls anything, nothing. So if you take like some CUDA kernels that were optimized for CUDA and you just copy paste them in SYCL and you run that, so you get like terrible performance. So as an example, so I was working for Microsoft Antares, and so I took like a CUDA kernel and copied it to SYCL, and I was like getting only 40 gigaflops because I realized like none of the loops were unrolled even in release mode. So just I think unrolling everything, like multiply the performance by a factor of 100, which it's a lot. And yeah, so I really think the issue is coming from the compiler because it doesn't have enough data on the GPUs that would behave to be able to figure out where to do the unrolling. So yeah, so I talked before about the issue of inlining, kind of inlining constant data. So when you're in SYCL, you can with C++ 17, you can do that with lambda context per lambdas, and you just context per stud arrays. So that allows you to have to declare globally like buffers and to get them inside of your kernels to unroll that loop and eventually just get some constant data, which will be cached by the kernel into the constant memory rather than having to use an accessor. But so yeah, these kind of things were able to like regularly like 15-20% improvement in the hashing library. And I would say like the biggest issue I had lately, it's with so it's not a word that exists in the language. So it's registerization, and that is the fact that on GPUs you don't have a stack. You don't have a on-chip stack. The stack is in the global memory, and you are accessing it like any global memory with latencies and so. And so you can't be accessing like local arrays with dynamic indexes, because the compiler just doesn't know how to map, like, I don't know, I to a register. You can't address a register with a number. Yeah, in hardware, it makes no sense. So usually what happens, as soon as you've got some arrays that are not always accessed using compile time deducible indices, the whole structure will be sent to the stack. And it leads to extremely bad code, especially when we have function calls, because it means when you call a function, we have to copy data from the stack to another stack. Yeah, it's a mess. And turns out that SYCL and DPC are implementing SYCL constructs like SYCL ID, SYCL range, and even vectors on DPC using arrays, which means that as soon as you ever like access a range or ID, not with a constant like 1 to 3, integral constant, but something else, your kernel ID will be on the stack. So just to know where you are, you will have to go to the main memory, and it's terribly slow. So yeah, and so I found a workaround to force array registration. Yeah, naturally that's the word, really. And basically it's like some recursive template that gets optimized away, thankfully, by the compiler. And that allows you to map to, that allows the compiler to see more optimization opportunities. So right now, there is a link to the implementation, but you'll get it later, I guess. And yeah, so right now you can pass anything. You can just, it's an accessor wrapper, say, and you access your ID vector, study array, study vector, SYCL vec, or even like C-style arrays, or anything that has a subscript operator, so that through that runtime index wrapper, and allows you to force the array to be in the registers, even though you are accessing with dynamic indexes. And so here is like an example. So on the bottom right, you've got the code. So you can see like on the first kernel, so with the blue line, I'm submitting. Just I'm accessing an array using braces, and on the last in the last kernel submission, I'm accessing using the wrapper I was talking about before. So at the left side of the screen, you've got the code that was generated. So in release mode and everything. So this is a PTX generated, and it basically uses, I don't know, like maybe 30 registers, 100 bytes of stack frame per thread. If you got like 30,000 threads, it's a lot. So it means occupancy and performance. And yeah, so you can see like every like call, you are storing like data to the memory. Yeah, and then you are reading and you are performing like the I'm %3, I'm sorry, the modulo operation, which can just be deduced at compile time, because that thing is always 0. If you look at the code, you can see like the array is 0 initialized, the coordinates is 0 initialized. So any index should always return 0. So using the wrapper I wrote, you can see that the code, the generated code, like it's not an up. I mean, it makes no sense actually to run that. It's always returning 0. And so I was able with that same wrapper yesterday to just like get like, once again, 2x performance benefit on a kernel I ported from CUDA. And yeah, honestly, I will open a pull request on that. It should be an optimization. The compiler should be able like to do itself. Like if you have an array of sub3, you see the compiler can just compute the index and assign a register like 0, 1, 2, even if it's not addressing with braces like PTX. Yeah, so I'm kind of confused why it's not doing that. But yeah, anyway, it can be done. You just need to access using the code I sent. Something else that really brought me like huge performance benefits was template metaprogramming, which often is criticized, but in HPC you don't really care about compile time because the code will be running for months, so it's fine. So the main recommendation and thing I did in almost all of the projects was to take away, to move the control flow out of the kernels, and so into the template parameters and using if const expr, you are able to get like kernels that are really tailored to a computation. And so you can, at the same time, by using if const expr, you can really statically remove function calls from your kernel. And so let's say, so I had that issue on the DPC project a few weeks ago. So there were some function calls that were never, some functions that were like used like in only like 5%, 1% of the cases, but that function had dynamic addressing inside. So it means that potentially that function was called by the GPU, but the runtime, the compiler wasn't aware to figure out when it was called because the logic was outside of the kernel scope. And so given the fact that there was like some dynamic addressing to some of the data, the whole data was going to the stack and I was losing performance. And so by tailoring the kernels and so removing function calls, the compiler just see clearer through the code and is able to perform new optimizations. And so I found that like a few days ago in SYCL 2020, now, sorry, C++ 20, you are able to do a reflection on types inside of kernel classes. So I use that when we're implementing some of the CUDA primitives. I'm like storing using unions to avoid atomics because on the CUDA, GPU can have like can store like a 64-bit word in a single time. So there is no need for atomics, which cause synchronization. You can avoid in some cases. Yeah, so you can just use that and have a template that changes depending on the input inside of the kernel. So here is the syntax. It's very messy, but that, yeah, you can use that for anything if you need. Yeah. Then I will quickly talk about strength reduction. So a big caveat with SYCL is that it is a 64-bit interface. No, not really 64-bit. So the data size types have to match for data marshalling reasons, between the host and the device, but the host is always 64-bit, and you can like compile DPC++ for 32 bits anyway. And so it means like you will probably be using size T everywhere because the spec is written with size T. It turns out like size T will be 64-bit on the GPU, but the GPU has only 32-bit addressing anyway. But there will be like an upcast to a 64-bit value, then to downcast to, I mean, like, yeah. Anyway, so just like turning all the addressing from size T to uint, like so in single place, I was able to get like 4 or 5% of performance increase in generated kernels by Microsoft Antares. And really, like this is these are useless instructions because CTA like IDX, the ID will never be like 64-bit. It can be in the hardware. So, but once again, that is a kind of issue of SYCL because you are targeting any hardware and you are not really always able to specialize the kernel. So I will be talking about that later sometimes. And then, yeah, you should also be checking like divisions, etc. So here is just the mapping for like some CUDA optimization flags you can have to have like fast railroads, etc. Things you can like fuse, multiply and add, and things like that, or like even control the rate count. So fuse obviously is not NVCC, so you don't have the same flags. So here is the mapping that works. Yeah, those what you would usually be doing in CUDA if you are doing that. And finally, if you are really requiring some like very specific CUDA features, you can always first check if it's implemented because it very probably is in DPC++. Or you can just using that syntax, you can be declaring like inline assembly that is only going to be compiled for when compiling the kernel in SYCL for the GPU. So right now, like with that function, you can have you can be preferential into the uniform buffer data. After a certain computation, you realize that while that data is constant. So yeah, you can write that. It works. Yeah, out of the box. And you shouldn't have to. But while it's not finished, you can write. It's not nice to write assembly. And yeah, so not to conclude, almost to conclude. There is a lot of on pronounce that word, but it's counterintuitive. There are a lot of counterintuitive things in GPU SYCL compilers, and you can realize that even so, by adding sometimes synchronization in a function, like which seems like a constraint, well, you get performance boost because you will use your whole cache lines, etc. So yeah, don't be conservative. Try crazy things. Sometimes it works. Like yeah. So I didn't have time to talk about that. But the wrapper I wrote like for registers has several implementations using binary searches, etc., to find the register. And turns out, even though the binary search has less instructions, so you are doing like log n operations, it's always slower than a linear search for small sizes, because every like check has a higher entropy, so you can like predict, the compiler can guess, can reorder anything. And so I really would like, I would recommend you to watch like Andrei Alexandrescu's talk. The speed is fine in the minds of people. It's really impressive, and you will see like a ton of examples where adding instruction and computation dramatically increases the performance. Like even before you saw that adding a wrapper, so which is function code, which is like I think 250 lines of implementation. Well, yeah, deletes your kernel because it allows compiler to optimize away. So yeah, it's not always smaller, better. But yeah, less assembly might be better. Anyway, yeah, and also there is a lot of things, optimization tricks used in libraries, such as if you realize you are submitting very, very small kernel, it's cheaper to bring the memory from the GPU to the host, perform computation on the host, and then send back the memory to the device, I mean, the CUDA thing, device, than performing the computation on the device. So you are able, once again, like able to get a very performance curve closer to NVIDIA what they have in their GPUs, because I guess are doing that via GPU and don't use the GPU. Anyway, yeah, and finally, I just want to talk a little bit about benchmarking and profiling. Something I saw a lot, and it's very, I don't think it's well handled by the DPC tool, is time measuring of kernels. So in CUDA, you are using, I mean, code is often using events, so which really tells you how many times the runtime spent running the kernel. And DPCT will translate that into like structural calls, which include the time, the overhead of the runtime, SYCL, and everything, which isn't really dependent on the code itself. So just by using the proper tools, so with this syntax, by enabling profiling on the queue, that's not optimization, but I was able like to like get like 15–20% better timings on the kernels, which is huge, because you often see like SYCL, which performs slightly worse than CUDA, but if you are using that, I mean, you are just not having the right benchmark. And yeah, it's unfortunate. I think it's, yeah, so just benchmark properly. So if you want to have something nice. And yeah, so the key takeaways are, I mean, I'm already like talking for way too long. So yeah, I would just say that templates are nice. You shouldn't be afraid of that. Think that you are targeting a 32 bits architecture in a 64-bit interface, which can be like, using like 64-bit things, and yeah, more code to be better. Yeah, so that's all for me. Yes. Oh, yeah,
Thanks, Michel. That was great. I think we can all give some applause emoji reactions for that. That was lots of information, lots of detail, and I think everybody appreciates that. So thanks for going through that. I appreciate we're on the hour now, but I guess Michel and I can hang around if anybody's got any specific questions